Now let's look at part B of example 8.2. A two-tailed test with alpha equal to 0.02. So part B, alpha is 0.02, and we have a two-tailed test. So we have our hypothesized parameter in the middle, and remember here, for a standardized normal distribution, the z-value there would be 0. Alpha is split out into two tails with a two-tailed test. So that means that in the lower tail, we would find alpha over 2, or in other words, 0.01 or 1% of the distribution. And in the upper tail, we would find alpha over 2, or 0.01 or 1% of the distribution. Now we're going to use table E, and this time let's use the table that has the positive z-values. We could use either, the table that uses the negative z-values or the positive z-values, because we would find a negative z-value to the left and a positive z-value to the right, but they would have the same absolute value since the normal distribution is symmetrical. It's exactly the same on the left side of the mean as it is on the right side of the mean. So in this case then, if we have 1% of the distribution in this tail, and this table is organized by the value that is accumulated, or the area that's accumulated up to a point, then we would be looking for 0.99 or 99% of the distribution. And what else does that mean? That means that 0.98 of the distribution would reside between these critical values. So I have an upper z critical value and a lower z critical value for a two-tailed test. So all the way from the beginning of the left tail up to this point that corresponds to this critical value, we would have 99% of the distribution. This 1% plus this 98%. Now this could be expressed as a proportion as 0.99. And when I look around in this table for 0.99, we find 0.9898 at 2.32 and 0.9901 at 2.33. 0.9901 is closer, so we're going to use the 2.33 value for these critical values. So we would have 2.33 as a critical value to the right and minus 2.33 as a critical value to the left.